Righty, good afternoon or good evening, Dr. Birch. This is going to be my recording for my test corrections. So I'm going to go ahead and start sharing on my iPad real quick. Start broadcast. Okay. So our first problem is going to be the series test questions. This is going to be problem number one. So first, let me show you what I did. I looked at this and I thought I could use the test for divergence basically via L'Hopital's method, right? So I looked at this and I said the limit as n approaches infinity of this series, 3n squared plus 1 over 5n cubed plus 3. This is what I did. I did bad math here. I applied L'Hopital's. I said 6n over, and this is where I messed up. I said 15n. Now from here to here, it should have been 15n squared. So I just messed up and left that off. And so because I did that, bad algebra or bad calculus there, I looked at that and I thought, oh, I could do L'Hopital's one more time and take the derivative once more on the top and bottom and end up with 6 over 15. And thus I thought, well, that does not equal 0. So by the test for divergence, this series diverges because I did this bad calculus right here and got it. What I should have gotten, sorry, if I were to have done L'Hopital's correctly, is I would have gotten 6n over 15n squared, tried it again, and ended up with 6 over 15n, all while, next, let me drop this, all while the limit as n approaches infinity. So this end up being infinity, and that goes to 0, which means that the test for divergence would have failed had I done it correctly. And this would have told me to use a different method. So switching to our more correct method, the second go around, I look at this and I think, well, as we're going towards infinity, this 1 and this 3 become a little bit more irrelevant. So as we're approaching infinity, those become irrelevant. We kind of end up with this, right? And from there, we can do two things. We can take this portion out and we can reduce the degree of the polynomials. So taking those out, we end up with, and reducing it, we end up with something like this. And this series we know diverges because by the p-series test, here p is equal to 1, and we know that p has to be greater than 1 for it to converge. Otherwise, it diverges. So from this, we can assume that this function is going to behave similarly. So we could use the limit comparison test with this series in our original series. Limit comparison test says if you take a series, b of n over a of n, this is the series we're testing. And this is the series that we know. Now, here we're going to be using the series 1 over n, And our an is going to be our original series, 3n squared plus 1 over 5n cubed plus 3. Now, setting that up, we have the limit as n approaches infinity of 3n squared plus 1 over 5n cubed plus 3 times the reciprocal n over 1. And we can just multiply that through, and we end up with, it's going to be 3n cubed plus n over 5n cubed plus 3. And because of our limit laws, we know that because these are polynomials of the same degree, we know that the limit is going to reach the leading coefficient, which is 3 over 5. And so since our limit is a value that is finite and positive, we know that the series that we just tested is going to behave in the same way that the series that we know. Therefore, by limit comparison test, with the series b of n is equal to the summation 1 over n, the series, oops, I don't need to write that. The series that we were given, 3n squared plus 1 over 5n cubed plus 3, diverges as the limit n over bn is equal to 3 over 5, which is equal to L, which is finite and positive. So that was the first question. So that is our answer. Now, for our second problem, it's a little bit easier to explain what went wrong. So, first off, it's something like this. I said, well, this is just bad calculus all around. I think I was just tired and kind of just got things backwards, honestly. So I said the derivative of ln 1 plus x is equal to 1 over 1 plus x, which is incorrect. It's backwards. It should have been the integral, right? And then I said, well, I know that 1 minus x is equal to the power series x to the n, and then I know that 1 over 1 plus x is equal to the power series, the alternating power series minus 1 to the n, x to the n. And so I kind of did something like, well, if I take the derivative of d dx of 1 over 1 plus x and the series on the other side, you'll end up with what we're looking for, which is actually just completely backwards from what we were actually trying to do in this problem. So I said this. That's what I did. And that's just completely backwards to what this question was asking. So I think I was just tired and not thinking correctly about what I was trying to do. What I should have done was something like this. Looking at this function, I know that 1 over 1 plus x, if I take the integral of that, I will end up with ln 1 plus x. Starting from there, well, I know that 1 over 1 minus x is equal to the power series x to the n. And then I know 1 plus x is equal to the series, alternating power series, minus 1 to the n, x to the n. Well, then all you really have to do is set them up. That. So I take the integral of 1 over 1 plus x, and then the integral of the power series on the opposite side. 0, infinity, minus 1 to the n, x to the n. On the left-hand side, we end up with ln 1 plus x, which is good. That's the function we were trying to represent in power series representation. And on the other side, we end up with summation n equals 0, infinity, minus 1 to the n, x, n plus 1, all over n plus 1 plus c. Now, at the beginning, when it said centered at x is equal to 0, that's what enabled us to get rid of our c. So x is equal to 0, thus c is equal to 0. So, final answer, ln 1 plus x, our series representation of that is equal to summation n 0 to the n plus 1 all over n plus 1. That is the final answer. So I think I was just getting it backwards and mixing up what I was supposed to be doing in this last part. So those are my test corrections. Thank you.